So, in the previous lecture, we have calculated the force on a part of a current carrying sheet. We have also before that calculated the force on a current distribution due to an external B field. What we want to do now is write this whole thing as a force arising from some sort of a stress. So, we wish to now to express these forces as arising from a stress produced by magnetic field. This again is very similar to a calculation that we did for stress due to electrostatic field. So, this is all to understand as to how the force due to a magnetic field transmits, creating a stress. That is what we want to do. So, to do that, we again write the force on some current distribution is nothing but integration dV j r cross B r, and this B r is B external that we may have applied plus B due to j. So, this is this field due to j itself and external field everything, right. If we integrate this, the internal forces due to j on each other, if we integrate over the entire j, will cancel. So, this calculates everything. So, we want to express this as the ith component of force arising out of some sort of a stress d s k t I k, where S is the area. I think just for convention, I was writing in the electric case this T k I. It is a symmetric tensor, so it does not matter, but just to follow a convention, I am just writing it like that, where T k I is the stress tensor. At this point, I would like you to recall that for electrostatic case, T k I was given as E k E I minus 1/2 delta I k E square. We will get a similar expression for B. So, let us do that. So, I want to derive f, which is equal to integration dV j r cross B r, which is nothing but integration dV j is 1 over mu 0 curl of B cross B r. Curl of B is j because this B is the total B due to external and due to JR itself. So, this is fine. And if I want to calculate f I, it will be equal to integration dV 1 over mu curl of B crossed with B ith component. And this is what we want to show is like a force arising out of a stress tensor. So, f I I am writing as 1 over mu 0 integration dV curl of B crossed with B ith component, which I can write using Levi-Civita symbol as 1 over mu 0 dV epsilon I j k curl of B jth component B kth component. Curl of B jth component I can again write using the Levi-Civita symbol as 1 over mu 0 dV epsilon I j k epsilon j L m partial L B m B k. And now, I will use this identity where I am going to write epsilon I j k epsilon j L m as epsilon j I k epsilon j L m with a minus sign in front, which will be equal to delta I m delta k L minus delta I L delta k m. And therefore, I get f I as equal to 1 over mu 0 integration dV delta I m delta k L minus delta I L delta k m multiplied by partial L B m B k. Now, I can carry out the summation over repeated indices and write this as 1 over mu 0 integration dV partial k on B I B k minus partial I B k B k, which I can write as 1 over mu 0 integration dV partial k acting on both B I B k minus B I partial k B k minus 1 over mu 0 dV 1 half d I B vector square. B k will give you B vector square, and 1 half comes because this is a square. Notice that this term partial k B k is nothing but divergence of B, and this is 0. Therefore, this term is going to drop out. So, I am left with f I is equal to 1 over mu 0 integration dV partial k B I B k minus 1 half partial I B square, which I can write as 1 over mu 0 integration dV partial k of b I b k minus half delta I k b square. Now, I define this quantity to be T k I, or which is same as T I k, and write f I is equal to, and this mu 0 is included here, integration d v partial k T k I, where T k I is equal to b k b I minus 1/2 delta k I b square. So, T k I can think of as 3 components of some vector T I, right. So, I can apply divergence theorem. So, using divergence theorem, I can write f I as integration d s kth component T k I. So, what have we done? Suppose there is this current distribution J r, and there is this net field B. If I want to calculate the force on this current distribution, let me enclose this in the some volume shown by black dashed line and calculate the ith component as d s k T k I integrated over this volume in which the current density is, and that will give me the force on this volume, and therefore, only on the current density, because force applies on the current density. So, that is the stress tensor due to magnetic field, right. So, T k I is the stress tensor or Maxwell's stress tensor due to magnetic field. And let us now solve an example applying this concept. Example. I am going to take the example that we solved in the previous lecture, and that is the force on the northern hemisphere due to the southern hemisphere of a uniformly charged spherical shell rotating with angular velocity omega equals omega z. So, we had done a similar problem of a shell applying force on the other shell due to electrostatic field, but we had solved it using electric field generated stress tensor. And if you recall that, what you will see is that what we had done, we had taken this shell which had surface charge density sigma, and we wanted to calculate the force on one hemisphere due to the other. So, what we had done is we had divided the entire space into this two volumes, and we calculated the force on the volume containing the hemisphere on which we wanted to calculate the force. And that force was arising because of the stress out here and we had this volume has area S k, and then we had just calculated that force using T k I multiplied by d S k and integrating it over this entire surface. So, we do exactly the same thing here. What do? We take this sphere which is rotating with omega, and we want to calculate the force on the northern hemisphere due to the southern hemisphere. Divide this whole thing into two halves. This is the upper volume, the lower volume, and this box extends up to infinity. So, if I calculate the force on this box, which will arise due to the stress T k I on this surface, which has this d S k, and calculate the total force, that will give me the force on the upper volume, and that force is applied only on the northern hemisphere. So, that will give me the force on the northern hemisphere. So, let us do that calculation. So, we have already written the magnetic field for this rotating sphere B n, that is for r less than r, is 2/3 mu 0 omega r sigma in the z direction, and B out is equal to 2 mu naught sigma r raised to 4 omega over 3 times 2 cosine theta r plus sine theta. And we want to calculate the stress tensor at we want to calculate the stress tensor on the plane containing the equator. So, we want to calculate this on xy plane, z equals 0 plane is the equator, divides the spherical shell into two parts. So, we want to calculate the stress tensor. So, calculate stress tensor on the z equals 0 or xy plane. So, here is the xy plane, here is the hemisphere on top, and here is the hemisphere on bottom. On the xy plane, theta direction is same as minus z. On the xy plane, cosine theta is cosine of 90 degrees, which is 0. Sine of theta is sine of 90 degrees, which is 1. So, we have the field B in z equals 0 plane is equal to 2/3 mu 0 omega r sigma z, and B out the z equals 0 plane is nothing but, I made a mistake, there was an r cube here and there was no 2 here. So, at z equals 0 plane, B out is minus mu 0 sigma r raised to 4 omega over 3 z. Both fields are in z direction, and therefore, only T x x T y y and T z z will be non-zero. Next, I am calculating the force on this plane which has only d s z. So, force d f x will be equal to integration d s x t x z d x x plus integration d s y t y x plus d s z t z x. On the surface, d s x is equal to 0, d s y is 0, t y x is 0 and t z x is 0. So, this implies that f x is going to be 0. Similarly, f y you can show is 0. So, the only component I am going to be left with is going to be in the z direction, and I am going to have d f z equals integration d s x t x z plus d s y t y z plus d s z t z z. But I have already shown you that t x z and t y z are 0. So, I am left with only d s z term. So, f z is going to be integration d s z t z z. So, only quantity I need to calculate for calculating the force on this hemisphere is going to be t z z, and t z z is going to be b z b z minus half b square, but b z equals b in the x y plane. So, this implies t z z is equal to 1/2 b square. So, what do I have now? I have this hemisphere and I have made this plane z equals 0. The only non-zero contribution comes from t z z, and t z z is equal to 1/2 b square. I know b inside, it is constant, and I know b outside. You have already written b in is 2 over mu 0, 2 over 3 mu 0 r sigma omega in the z direction, and b out is equal to minus mu 0 over 3 r sigma omega in the z direction, or r raised to 4 divided by r cubed. So, the net force F is going to be 1/2 b in square, it is a constant, times pi r square with a minus sign, because d s z is in the negative z direction and t square is a positive number, plus, and again I am going to pick up a minus sign because d s z is in the negative z direction and t z z is positive, 1/2 b out square integrated over 2 pi r dr is symmetric from r to infinity, and that is going to be your answer. So, this is going to be equal to minus a half b in square is 4 9ths mu 0 square r square sigma square omega square times pi r square minus 1/2 for b out, I am going to have mu 0 square over 9 r raised to 8 sigma square omega square integration 1 over r raised to 6 2 pi r dr from r to infinity, and there is a factor of 1 over mu 0 also, which comes in the definition of t. This is going to be minus 2 pi by 9 mu naught square r raised to 4 sigma square omega square minus pi over 9 mu 0 square, or mu 0 square 1 mu will go away, mu 0 r raised to 8 sigma square omega square integration 1 over r raised to 5 dr r to infinity. You calculate all this, and this comes out to be minus pi by 4 mu 0 r raised to 4 sigma square omega square, which is the same answer as obtained earlier. By calculating ds k cross b n plus b out divided by 2. So, we have done this calculation of the force on one hemisphere through Maxwell's stress tensor by calculating the force on this entire volume due to the stress tensor generated on its surface. So, to conclude this lecture, we derived the expression for magnetic stress tensor and used it to calculate force in an example. Thank you.